Now that we've done ice tables with looking at systems in solutions and working with concentrations, we can also do equilibrium calculations using ice tables or using just our K EQ formulas that we're used to, but we can do it with gases and partial pressures. So we won't always necessarily have concentration. We can also do the same types of work with partial pressures of gases. So any gas system at equilibrium, okay, with the same equation has something called a Kp. Now Kp is the equilibrium constant, but in terms of partial pressures rather than concentration. But it's basically equivalent to Keq. It's the same idea. But instead of taking the concentration of C to the power of little c, we're looking at taking P, the partial pressure of that particular gas. So let's do an example here where we're looking at the system of nitrogen gas plus oxygen gas makes nitrogen oxide, or nitrogen monoxide, I should say. Okay, if Kp is 4.15 for the system and there are partial pressures of nitrogen gas of 1.23 atmospheres and partial pressure of nitrogen monoxide of 5.35 atmospheres at equilibrium, determine the partial pressure of the oxygen gas. So let's pick out all these bits of information that are useful to us. So first of all, we know that Kp is equal to 4.15. Now Kp doesn't have any units, so 4.15. We know that the partial pressure of the nitrogen gas is 1.23. So P of N2 is equal to 1.23 atmospheres. We also know that the partial pressure of the nitrogen monoxide, so NO, is equal to 5.35 atmospheres. And this little bit where it says at equilibrium, that's really important. Just like how with concentration, we only ever put equilibrium concentrations into the equilibrium constant expression, this equation. It's the same with pressure. So we only ever use pressures at equilibrium to go into that equation. It says determine the partial pressure of oxygen. So we're looking for the partial pressure of O2, some number, and it will be in atmospheres. So let's start by taking this equation and we're going to write out the equilibrium expression in terms of partial pressures. So Kp is equal to, still going to go products over reactants, but instead of concentration, we're looking at pressure. So the products here, okay, are NO. So we're going to take the pressure of NO, and that's going to be squared because of the 2 that's in front. So that's the same as with the concentrations. The coefficients become exponents. So products over reactants. So on the bottom, we're going to have the the partial pressure of N2 gas times the partial pressure of oxygen gas. So here we've got products over reactants. The same way as before, we're just using these partial pressures instead of concentration because they're gases. So now we can sub in all these numbers that we do know into that equation. So Kp is 4.15 equal to the partial pressure of NO was 5.35. So 5.35 squared divided by partial pressure of nitrogen was 1.23 times the partial pressure of oxygen, which is our unknown thing that we're going to be solving for. So now we need to find this number. So we need to isolate it, just regular algebra. We're going to multiply it over to that side. So that gives us 4.15 times the partial pressure of oxygen equal to 5.35 squared divided by 1.23. Now to get this PO on its own, we need to take this 4.15 and divide it on the other side and move it down. So that's going to give us PO2 equal to 5.35 squared divided by 1.23 times 4.15. Now we just have to type this into our calculator, and it should give us 5.6073. We need to round to the correct number of significant figures. We have 3 significant figures all the way through, so we're going to keep 3 at the end. 5.61, and our unit for partial pressure in this particular question, okay, is atmospheres. So that gives us the partial pressure of O2 being 5.61 atmospheres. So we can finish this off with a final statement. Therefore, the partial pressure of oxygen is 5.61 atmospheres at equilibrium. Okay, so these types of questions work the same as the ones with concentration in solutions. They're just gases, and we use partial pressure instead of concentration. There's one final type of these equilibrium calculations that we're going to go over, and that is looking at what happens when the KEQ value is really, really small. So if your equilibrium constant for a particular reaction is equal to or less than 10 to the power of -4, okay, you can use something called approximation, where we kind of get a bit of a shortcut when this happens, and that can help us solve questions, because what this means is that a reaction proceeds in the forward direction very, very, very little. Okay, so we're making a very small amount of our product compared to how much reactant we have. So let's take a look at this first example to see what that actually means for us. Okay, at 727 degrees Celsius, the equilibrium constant for the dissolution of iodine gas molecules into I atoms, okay, is 3.8 times 10 to the -5. This is a very, very tiny number. Okay, so this is, let's say, 2 significant figures. Okay, this is also our KEQ value. So we can kind of keep that in mind. If the original concentration of the iodine gas is 0.2 moles per liter, so this one has 3 significant figures, just make note of that. What is the equilibrium concentration of the iodine atoms? We're going to start by writing out the reaction equation. So in this, we're looking at I2 gas, okay, forming I atoms as gas, and to balance it, we need to add a 2 in front. So I2 equals 2 individual I atoms. The KEQ for this reaction is 3.8 times 10 to the -5. Okay, this is very, very small. Very small, which means that there's almost none of this actually being made. Most of the reaction is over here. Most of what is present is going to be the I2 gas. Okay, very little is coming over here. We're going to set up our ice table. Okay, so we'll kind of go through the steps here. Step number 1 is to set up our ice table. Make sure I'm still in the field of view here. There we go. Okay, initial, change, and equilibrium. Then the parts of our equation, we have I2 and plane I. Okay, it says in our question here that we're starting off with 0.2 moles per liter of the iodine gas. So our initial concentration is 0.200, and we're starting off with no I atoms. Okay, our change line here is a 1:2 ratio. So minus X of our reactant and plus 2X for our product from the 2 there. remember our equilibrium line here, E equals I plus C. So this is equal to 0.200 minus x. This is equal to 0 plus 2x. And we need to solve for what x is to determine what the concentration of this is at equilibrium. So there's step number 1, set all that up. Step number 2, okay, following the same as we were doing before, we need to write out our equilibrium expression. So KEQ equals products over reactants. And remember, the exponent comes from that coefficient. So products over reactants. We can sub in this stuff that we know. So here we've got 2x squared for the squared there. And then this bottom line is 0.2 minus x. Now at this point, if you tried to solve this, you wouldn't be able to. You wouldn't be able to figure out what x is with this mixture of like integers and sort of algebraic stuff. Like you can't, when you FOIL that out and you make this 4x squared, and you can't, there's no way of solving what x is. But we can figure it out, and this is how. If we look back at this KEQ, this is very, very small, okay, which means, so we expect, based on that, okay, x is going to be very small. Okay, this change, this x we're creating, is going to be so little because this reaction proceeds in the forward direction very little because this number is so small. Okay, so x, we expect x to be very small because KEQ is so small. What that means is, so therefore, 0.200 minus x is basically equal to just 0.200. Okay, when it comes down to it, compared to 0.2, whatever this x number is going to be so small that when it comes down to rounding out the significant figures back to 2, it's going to end up being the same number. It's going to be 0.1999 something. Right? So it's going to be so close that when we round to the correct number of significant figures, it's just going to round back to 0.2 anyway. But anything compared to 0 is big. So x compared to this 0.2, x is really, really small. So this is what we call negligible, which means that this is now negligible, which means that our equilibrium concentration of the I2, oh, that bracket should be on the other side of that. My apologies, I2, there we go, is equal to 0.200 in the end anyway, moles per liter. But this 2x compared to the initial 0, it is something that's going to be significant because anything compared to 0 is significant. So we can still solve for what this top x is going to be. We just don't actually end up needing that x anymore. What that means is we can take our equilibrium expression. So we're going to solve, or we're going to sub in this 3.8 times 10 to the negative 5 for KEQ. So 3.8 times 10 to the negative 5 is equal to, we can put that squared in, so we're going to get 4x squared divided by 0.200. So I'm getting rid of that minus x there because of the approximation that we get to do. Now it's easy to solve for what this x is. We're going to take this 0.2 number, we're going to multiply it over onto the other side, which we got 0.200 times 3.8 times 10 to the negative 5 equals 4x squared. We're going to divide the 4 on both sides to get rid of it on that side. That gives us x squared is equal to 1.9 times 10 to the negative 6. So that's that times that divided by 4. We'll take the square root of both sides to get rid of that squared symbol. And that's going to give us x is equal to 0.014. Oh, 0014, my apologies. 0.0014. Once we know what x is, step number 3 is to sub that x into our ice table and determine those equilibrium concentrations. So here, even if we were to sub the x in, 0.2 minus 0.0014 is just going to give us 0.2 again. So we don't need to really do anything with that. But the question asks us for the concentration of I2. So here we have 0 plus 2 times 0.0014. That's going to give us 0.0028 moles per liter as our equilibrium concentration of the iodine atoms. So we can finish this off, sort of step number 4 here with a therefore statement. Therefore, at equilibrium, the concentration of I is 0.0028 moles per liter, and we're rounding to 2 significant figures for that final answer. So when is the approximation valid? Let's make a quick statement here so that you have it in your notes. Okay, so when is approximation valid? It's valid when x is so small, okay, it is negligible compared to the initial concentration okay, which is basically told to us by what KEQ is. So when we get to do this, when KEQ is very small, okay, less than or equal to the magnitude of times 10 to the power of negative 4, okay, or smaller, which would be this number getting bigger, greater negative. All right, and we'll do some practice in class tomorrow. See you then.